hopefully this would be available on YouTube soon after the event. And thank you very much for coming. My name is Mohammed Ijaz. I am serving as a chair of Aberdeen ICorr committee in Aberdeen, and I'm convening today's event. So I welcome you all for this. Welcome you all on March 2021 ICorr Aberdeen event, which is quite. It's been quite nice year for us actually. Apart from COVID, of course, the webinar sessions we have been doing has been quite nice and quite active, and we have been having quite huge attendance, and it's been quite appreciated. Thank you very much for joining us today evening. We have been having a very good response from the audience from all over the world. We have got very well attended ICorr webinars, and those are actually available in Google site as well as in the YouTube. If you are willing to actually look back on any of the events, please do so on YouTube. And the advertisement is usually done in icorr.org/Aberdeen. And we have got our own resource center in google.com/site ICorr ABZ. And we usually announce all the events in LinkedIn as well. So please feel free to join us. And with that, I would like to actually thank all our support from our sponsors. We have got quite a few Aberdeen branch sponsors that are highlighted with logos up here. And there are quite a few gold sponsors that are named here, as well as sustaining sponsors for ICorr Aberdeen. And we would like to thank everyone for supporting this event. And this is our team. Without these people, it wouldn't be possible for us to organize all these events. And I would like to thank all of the committee members who are supporting in the background as well in the front end anyway. So I'm actually just basically presenting this, but the whole work is done by the whole team behind me. We have got quite few people who are here today with us, but if you are interested in sponsoring us or advertising on ICorr branch, please feel free to contact us, any of us in the Aberdeen committee or at icorrabz@gmail.com. Before I introduce our today's speaker, who has been thankfully joining us to present today's event, I would like to request all of you to keep your mics muted, and please keep your videos off to save the bandwidth. And if possible, please put all your questions in the chat session on the right. Human, after the presentation, will take over, take all the questions and put them forward to George. Hopefully we would have enough time to answer all of them, but if we don't, then we will request Dr. George to actually answer on one of the slides, and we will put forward those slides in our Google website. With that, I would like to introduce our speaker for today. Is Dr. George Sergi, who is Technical Director at Vector Corrosion Technologies. Dr. George is heading the Research and Development Department, developing products for durability of concrete, steel reinforcement protection, and corrosion mitigation techniques for the civil engineering and construction industries. He has authored several international patents and has developed novel products for corrosion protection of steel and reinforcement. Dr. George holds a PhD in corrosion of steels in concrete and was formerly technical director and head of corrosion at Building Research Establishment in UK and technical director at Artisan Material Services Limited. He is editor of Construction and Building Material Journal, and he is member of Cathodic Protection Committee GAL 603, assisting in the editing and publication of BSI and EN standards. With that, I would request you all to put your hands together virtually. Welcome Dr. Sergi. And take over, sir.
Okay, thank you very much. Okay, thank you for the introduction. Can I just go straight in now?
Please.
Yep. Basically, I'm just going to go through some results that we've been receiving or collecting over the last 20 years, primarily from a site here in the UK, but there have been other areas where we've been monitoring. So I'll start a little bit about the background of Galvanic technology. This is a galvanic anodes that we've started developing maybe 30 years ago. At the time, I was at Aston University, and then I followed it through, basically now joined vector corrosion technology. I've brought over the technology, and they asked me to join them to continue the research and development. So I'll look at over the 20-year results and then try and highlight the lessons that we've actually learned over that period, or over the results that we've gained, that allowed us to determine what we call an aging factor and see how systematically the current output of galvanic anodes is reduced over time. And knowing that and other things that we've learned, that's enabled us to have an enhanced design concept. You can predict how the anode will be behaving 20 years down the line, so you can design that into your system. And I'll finally talk about fusion technology, a very recent development that we've achieved in the last 2 or 3 years, which combines ICTP, the impressed current cathodic protection side of cathodic protection, with the galvanic anode technology. So, cathodic or corrosion prevention is basically to prevent corrosion from initiating, rather than stopping it after it's started. There's no existing criterion for that in the standards, although we've been looking at that. We are actually looking at EN 12.6 or 9 recently to try and deal with that necessity. But there isn't any standard at the moment. The only thing that it's mentioned in the standard is that the current density necessary to prevent corrosion from initiating is between 0.4 and 2 milliamps per meter squared. And that is much lower than the level required to stop ongoing corrosion activity. And that's more like 2 to 20 milliamps per meter squared. So it's an order of magnitude lower current requirement. Now, why am I talking about corrosion prevention? Well, one of the initial problems that people who are repairing concrete construction were finding was that when they carried out a repair, a patch repair, i.e. remove any cracked concrete, remove contaminated concrete around the steel, that will make a very good repair, and it looked wonderful. But corrosion would initiate at the periphery of the patch repair very quickly. 2 to 5 years later, they would have to come back and repair the adjacent area. And therefore that meant that they were sort of chasing their repairs. You can have one patch repair, then you move along to the next bit and the next bit and the next bit. Obviously there was a problem. There was something that was happening that wasn't stopping the corrosion close to the patch repair, not in the patch repair itself. And that's the problem that FOSROC came to us when I was at Aston University, saying, well, we've got an issue with our patch repairs. We think our materials are very good, but few years down the line, we have to go back and reapply patch repair to adjacent areas. And we came up with the solution that what was actually happening. Well, first of all, we tried to understand the issue, and what was actually happening was when you carry out a patch repair, you have now forced the steel within the patch repair to become the cathode being the area that's non-corroding, but drives the anode being the area that is corroding. So initially, what was within the patch was the anode, and therefore the corroding region. So steel was corroding. We now fixed that. We forced it to become an anode, a cathode, I beg your pardon, which means that any slight contamination of the periphery of chlorides, perhaps, or carbonation, or a change in pH in the concrete, would force the surrounding steel to become anodic and therefore start to corrode. And that was basically the principle. It's now called the ring effect. It's been known for many, many years. And our solution was to attach this type of anodes around the periphery in order to maintain that region inside the patch repair as anodic. So the anodic areas are now these little anodes. They're the corroding bits that are corroding sacrificially, and they protect the surrounding region, particularly the periphery of the patch repair. But there had to be a bit of development to try and convince the zinc that we were using as the core material. Zinc is obviously more electronegative than steel, and therefore will preferentially corrode if you couple it with steel. But the zinc needs to remain in an active condition. If you put zinc acetate inside concrete at pH 12.5 or roughly that, you would see that it would start to passivate. It would form calcium byproducts. And that would act as sort of a passivation layer on top of the zinc, and soon the corrosion of zinc would stop, and therefore you're not really protecting the steel reinforcement. So we had to encase it in a cementitious material that will maintain the activity of the zinc. And the way we achieve that is to include a saturated amount of lithium hydroxide, i.e. lithium hydroxide powder mixed into the cementitious material that will maintain the pH well above 14, and it will keep it at a constant pH because it's a saturated solution. It means that it acts like a buffer, and therefore that will continually maintain the activity of the zinc product. As well as that, we had to introduce a porous medium so that any corrosion product would be able to migrate into the surrounding material. And this trial I'm going to talk about, this was it's over 20 years now, and it was a typical patch repair in a bridge in Leicester in the UK. We removed 2 adjacent areas. We removed the cover concrete, exposed the steel that was corroding, and then attached 8 anodes around this area and 4 anodes around this area. As you notice, it's at the periphery of the patch. But instead of connecting the anodes directly to the steel reinforcement, we took the connection into a junction box, connected the junction box to the steel reinforcement, and therefore we were able to turn on and off the galvanic anodes. That allowed us to measure the current that flowed between each individual anode and the steel. It also allowed us to turn off the system for 24 hours and watch how depolarization would develop over the time, and also look at the depolarized potential 24 hours after disconnection. And this is essentially the current output that we saw over the years of each individual anode. 12 anodes there. You can see that one of these is not particularly happy, but all the others are more or less diminishing in intensity with time. We looked at how much zinc we actually consumed over the time period. We did that both ways. I measured the amount of charge that was delivered by the individual anodes, used an efficiency factor of about 70%, and determined how much zinc was consumed using the Faraday equation. And we saw that after 20 years, we roughly used about 60% of the zinc within the individual anode. You can see number 3, which is the one that was struggling. Then at 10 years, we actually took out some of the anodes, not in fact the ones within the monitored area, but there were adjacent patch areas that we installed at the same time. We took one anode out to have a look and see how it was consumed. And we could see that the consumption was relatively smooth. You lost zinc. That was the original zinc outline. The space between that was evacuated, if you like, by the zinc product was filled with corrosion products, primarily of zinc oxide. But we also noticed that the zinc oxide was able to migrate into the pore structure of the cementitious material, quite a long distance, particularly on this side where you had more of the corrosion, quite a distance into the encasing mortar. And that was what was actually being hoped for, because we know that zinc in a very high alkali environment, when it corrodes, the corrosion products remain soluble. They're zincate ions, and they're able to migrate within the pore structure. They then obviously, when supersaturation is succeeded, they then precipitate out as zinc oxide. But we can see that we are able to move the corrosion product quite a distance away. That means that you're not really concentrating them too much at the interface, and you're still allowing the electrolyte to be in contact with the zinc, and the corrosion of the zinc will continue to occur. Looking at the depolarized potentials, i.e., once we've turned off the current and then looked at the potentials of the steel reinforcement 24 hours later, we could see that with time, the potentials that moved in a positive direction, and therefore become passive. Anything above -200 versus copper sulfate is normally considered to be passive. There's a slight issue there, which I'll talk about a little bit later. Now, when we started analyzing the current output, and we converted it into charge delivered, cumulative charge, as an average of all the anodes, we could see that up to about year 6, the line fitted what we predicted by modeling. So this particular line reflects a model that would start with a current density, current output for each anode of 250 micrograms. And the only thing that's reducing the current is the fact that you're reducing the surface area as you're shrinking basically the zinc anode. But at 6 years, that tended to deviate away from that line into sort of the second line, which fitted a model of more like 100 micrograms. And then we had a third deviation, but we were able to work out that deviation as when the lithium hydroxide, saturated lithium hydroxide, had diminished, and therefore there was no longer a saturated amount of lithium hydroxide, and the pH started to drop. So that was due to the drop in the pH. But what was that reduction due to. Now, we've assumed since that it's because the corrosion products have actually accumulated to such an extent that they started tightening up the structure, and therefore the electrolyte was finding it more difficult to electromigrate and therefore resisted the current flow. But both of these things could be dealt with. Here you can deal with this one by increasing the amount of lithium hydroxide. And we've done that with subsequent designs where we increased the lithium hydroxide content by up to 10 times. This could be dealt to an extent by increasing the porosity of your encasing mortar. The fact that the lithium hydroxide saturation was lost was also seen by another parameter that we were measuring. And this was after the 24-hour period when we disconnected the anodes. At reconnection, we would measure the current output of the anodes within 5 seconds of reconnection. That tells you indirectly the power that remains into the galvanic anode. And obviously the first 14 years or so, that was well above 1 milliamp per anode. But suddenly after about 14 years, that dropped significantly down to about half of a million. And that coincided with the time when the lithium hydroxide saturation, or the lithium hydroxide had been consumed and the pH started to drop. Looking at another anode, this one from the patch after 20 years, we could see that this is the corrosion product build up around where the actual initial zinc surface was. But removing that, you could see that there was still quite a large zinc core that was available for further corrosion and further protection of the steel reinforcement. So this was after 20 years, as I said, and we were able to work out the efficiency, i.e. the amount of zinc that was consumed theoretically by using Faraday's law compared to the mass loss that we had of that particular anode, and we found that the efficiency was roughly, or at least 70%. So 70% of the zinc was used to produce the current that was delivered to the steel. 30% is lost due to self-corrosion. Okay, looking again at the potential map at around 20 years. Potential map is when we take measurements of the potential on the surface of the concrete around the patch and beyond. These are the patch areas within that red line, the 2 patch areas. And we can see that the potential within those patch areas was, in fact, was positive in some cases. And outside the patch repair, mainly they were below 200 millivolts. But there was an area, quite a distance between the two, that was showing signs of corrosion. And we noticed that there was actually a crack developing within that region. Looking at it at 15 years, we could see that there was a sort of a hairline crack that was just beginning to develop. This is the one patch area, the other one is over here. So the crack was actually developing. So at that time, at about 15 years, we were not producing enough current to control the corrosion in that region. And that eventually became thicker at 20 years. And we could actually see that very clearly and moved into the patch repair. So up to 15 years, we could claim that we were able to maintain the patch repair in a good condition that did not require anything further. Now we're in a position where we need to go back and do something to that patch repair. And if we look at the current, the mean current density over time, over that period of time, I mean, you could see that at 14 years, that's dropped considerably. But nonetheless, we could see that if we plotted on a logarithmic scale, the decrease in the current was actually exponential. So you had basically a straight line relationship. And we could predict from that, well, we could determine, if you like, an aging factor. The aging factor being how quickly the current halves from its original value. So in this case, we saw that at 7 years, it roughly halved, and 7 years more, it halved again, and so on. So there's an exponential decline of current density, consistent with the half-life principle. That makes things quite easy in consideration, because you can then try to design accordingly. Now, what else did we learn? The current density on this occasion halved every 7 years, and we term that the aging factor. So you obviously want to be achieving a higher aging factor than 7 years. Humidity and particularly temperature modifying the current output significantly. And you would have noticed that the current was not obviously totally exponential, but it went up and down depending on whether it was summer or winter. Now, since then, we've had a look at about 12 or 13 other situations. This first one is the one that I talked about in detail. We had an aging factor of 6.9 years. The spacing of the anodes was, i.e. the distance between the centers of each anode, was 600 millimeters. On an adjacent one, the same place, but in a column, the spacing was 750 millimeters, even wider. And we only achieved an aging factor of only just over 4 years in that case. But it tends to be related to that early current density. So in the case of the one that I talked about frequently, sorry, every time I touched, we were talking about an initial current density of about 0.25 milliamps per anode. In the adjacent one, that was at the spacing of 750, everything else was the same. It's the same concrete structure, the same amount of steel, therefore the steel density is very similar. The environment is similar. The initial current from exactly the same anodes was 0.5, double the current output of the first lot. And that early forcing of the anodes to deliver a high current has not allowed the corrosion products to migrate into the pore structure sufficiently quickly. So they started to block the interface between the zinc and the mortar. And that induced a reduction in the current output, which resulted in a lower aging factor. You could see that we were able to improve that considerably up to about 14 years, simply by reducing the spacing of the anodes. We were now asking the anodes not to work as hard, even though these anodes were double the surface area of these anodes. We maintained the current output about the same. Therefore, they were asked to work less hard at the beginning, with the result of achieving a better aging factor. And so on. These are more examples of the aging factor. We can see overall we achieved about 10 years, although on occasions we had 14 or so. So we now know which scenarios would give us the best aging factors, i.e. the longest period before the current reduces by half. Now, when I looked around in the literature to see how other anodes, remember these are alkali activated anodes, there are halide activated anodes, chloride, bromide, and as such. I could only find 2 examples of results that were published, and I determined the equivalent aging factor of those. I couldn't find anything beyond 3 years, so There's a clear difference between alkali activated anodes, which allow the corrosion products to migrate, and the chloride activated or halide activated anodes. Again, they use zinc, but what happens is zinc corrosion products are not soluble because the pH is quite low, and that tends to accumulate very quickly around the zinc motor interface. That subsequently reduces the current flow. And just to highlight how that aging factor can now be used, it gives us a lot more confidence of predicting where we want to be. So if, for example, we're looking for a current density of around, say, 0.4 milliamps per anode or per meter squared after 30 years, we know just sort of by using the aging factor that we need to start at around 2 milliamps per meter squared. Now, if you use the equivalent or the alternative halide anodes and start it at 2 milliamps per meter squared, you'll see that the current output would diminish so quickly that you're hardly producing any current even after sort of 15 years. And just to show it in a slightly different way, if our objective is to maintain a current density of 0.4 after 30 years, as I said, we need to start at around 2 milliamps per meter squared for the alkaline anodes, but well over 10,000 for the halide activated. That obviously is an impossibility. So just a summary, the surface life of existing galvanic anodes is expected to be at least 15 years and possibly 20 to 30 years. We're more confident that we can get to 30 years now with new technologies and the improvement that were made to the anodes from learning of our mistakes, if you like, or understanding the behavior of anodes. Current output of galvanic anodes is sustained for many years with a gradual exponential drop at a measured rate. And that measured rate we are now calling the aging factor. So the higher the aging factor, the better the performance of the anode. And the aging factor can be built into the design of the anode system to predict minimum surface life. And enough knowledge has now been gained about anode behavior over time to allow design to a required level of steel protection. So just by knowing how your anode would diminish its response or its current output over years, you can, as I showed in the examples, you can say, well, if I need a current density of X at year 30, then this is the current density that I need to start at. Okay, so going on to new developments, and this is what we now call the fusion technology. It's a two-stage protection. Now, the one stage is obviously the galvanic protection that we've now almost perfected and we understand very well. But we wanted to have an impressed current element at the beginning. And the main reason for that was to try and stop corrosion. So if we are able to arrest corrosion with an initial high charge using the ICCP anodes, we can then maintain that passivity of the steel just by using a lower current density, which I mentioned at the beginning, called cathodic prevention. So an order of magnitude lower current density, and that can easily be achieved by the galvanic anodes. Just as I said, maintain the passivity of the steel long-term by using galvanic anodes. So what was the background to that development? Well, we know that when we apply polarisation to the steel, i.e. cathodic protection, and the chloride ions being negative and the steel being also negative, they start to move away from the steel. Chlorides are the main corrosive element, if you like, when we come to steel reinforced concrete. Equally, we start producing hydroxyl ions at the steel surface because of the cathodic reaction. As long as you have oxygen and water, you will produce hydroxyl ions. So that hydroxyl ions would increase the alkalinity around the steel reinforcement. And that total result is that you are continuously reducing the chloride to hydroxide ratio. And therefore, the corrosion risk of the steel reinforcement. There is actually a critical chloride to hydroxide ratio below which there's no more corrosion. So the attempt really is to try and reduce the chloride to hydroxide ratio fairly early on in the application of cathodic protection to be able then to switch over to cathodic prevention. And we've seen that in the lab when we looked at ionic concentrations when we applied current. This is perhaps a slightly exaggerated one. We had a current density of, I think, about 50 milliamps per meter squared. But you can see that demonstrates clearly that what happens to the ionic concentration of the steel surface. This is the bulk of the concrete. This is the steel surface. And we can see that we are attracting sodium potassium ions towards the steel. We are repelling the chloride ions away, and we are producing hydroxyl ions. The result is that you are increasing your sodium potassium hydroxide concentrations around the steel reinforcement. And just as a sort of a summary slide to show the total alkali amount that you induce around the steel reinforcement when you apply this current, this negative current to the steel, and that you are reducing the chloride concentration. Therefore, the chloride to hydroxide ratio has reduced significantly compared to where it was at the beginning. What we also found was that if we induce a current to the steel reinforcement, the amount of alkali increase was actually dependent on the current density that we were applying. So at very high current levels, we were getting extremely high alkali concentrations. But even at a relatively moderate 20 milliamps per meter squared, which is what we apply normally as the top end of cathodic protection, we were still getting quite a significant increase in alkali. And it's really that alkali increase, the realkalization, if you like, of the acidic areas that have been produced when corrosion has been occurring, that tends to reverse the corrosion process. So we tried that out in the lab. We made some small specimens, little mortar specimens where we've had a steel plate which was masked all around apart from a central ring. And we introduced chloride contaminated mortar in the center of that, away from the edges so that we could avoid crevice corrosion. And we then applied, using a small mesh MMO coated titanium mesh anode, we applied a current density, cathodic current density to the steel reinforcement. And what we found was that depending on the amount of chloride that we've contaminated the sample with, if we only had 1% chloride, and in fact that's slightly misleading because in the lab it's very difficult to induce corrosion at 1% chloride, although in practice that happens very regularly. In the lab, using small samples, and you tend to make them a lot better than what you would make them on site. Corrosion is very difficult to induce, but nonetheless, within a few days of applying a small current, we were able to stop corrosion, and the steel was passive. At 2%, it took longer, and at 3% chloride, it took longer to repassivate the steel. And this was applying a current density between 20 and 40, 30 milliamps per meter squared. to the steel reinforcement. Another way to show it really is that if you compare two samples, one that was, both of them had 3% chloride in this case, one that hadn't had any current applied to it continued to corrode over a lengthy period, whereas one that was polarized and had 30 milliamps per meter squared current applied to it over a short period of time, then the steel became passive very, very quickly. And that's just another slide showing how, in every case, you were able to induce specificity of the steel reinforcement, even though there was a high corrosion rate at the beginning. Okay, what we found then by extending the experiments was that the level of depolarization that was achieved. Now, bear in mind that the standard asks you to maintain a depolarization level when you apply a cathodic current of 100 millivolts, otherwise you're not complying to the standard. Now, we've pre-corroded these samples over 2, 4, or 6 weeks with an anodic current density of 20 milliamps per meter squared. And we also had various levels of chloride, 2% and 4%. The samples had corroded so much that even though we were applying more than double the amount of current density that we would normally apply for normal cathodic protection applications, it took a long while before we could achieve 100 millivolt depolarization. And in some cases, it needed a lot of initial charge to achieve that. But nonetheless, there was a considerable improvement every time or rather, the higher the charge that we induced onto the steel reinforcement, i.e. the longer the application of the current, the more successful we were there with our depolarization potentials, eventually achieving close to 200 millivolts per meter squared, or 200 millivolts a meter. Similarly, if we have a look at the depolarized potential, i.e. the potential 24 hours after we switched off the applied current, so we allowed them to rest for 24 hours and measured the polarization potential previously, but also the depolarized potential, the rest potential. We saw that obviously at the beginning the potentials were very, very negative, indicating that the steel was corroding quite a lot. But with time, and it was almost linear, the potential became more and more passive, and moved towards passive regions. And we were able to calculate how much current density we needed, or how much charge delivery we needed to be able to eventually arrest corrosion. And we found that at 50 milliamps per meter squared, for example, at 2% chloride contamination, we were able to do that just by 65 kilocoulombs per meter squared application. Whereas for the same level of pre-corrosion, if you like, and chloride level, at the lower 30 milliamps per meter squared, we required 120 kilocoulombs per meter squared. So it was easier to passivate if you applied a higher current density. But of course, 50 milliamps per meter squared tends to get the cathodic protection engineers slightly nervous, because it's considerably above the 20 milliamps per meter squared that appears to be allowed in the standards. So we tended to focus more on the 30 milliamps per meter squared. And if it's over a short period, then that tends to be more acceptable. Okay, so a two-stage process is feasible to control reinforcement corrosion. Stage one is obviously to arrest corrosion and achieve passivity of the steel by applying an adequate initial charge. And then this is stage two, where you can continue to maintain the passive state of the steel over the longer term. by applying a smaller cathodic prevention type current of between 0.2 and 2 milliamps per meter squared. Okay, so it's basically a diagrammatic representation of the two-stage process. Initially, we've got chlorides and we've got corrosion and cracking and so on. If you apply very high current at the beginning, then you're increasing the hydroxyl ions around the steel, which tend to start forming a barrier. The chlorides then move away. And then all you need to do is maintain that barrier using a lower current density. And the chlorides would tend not to get close to the steel because they are charged negatively and the steel is starting to And this is basically the product. It's just a small encasement of in a cementitious material that again is saturated with lithium hydroxide, and that maintains the alkalinity for the galvanic element of the unit. But we have an ICCP element, essentially a voltage control, which is a battery. So a battery, for the best cases, we use 3.6 volt batteries, but you can use 1.5 volt batteries. You can use any voltage you require, a combination of batteries or whatever. But essentially, you need a battery to maintain a high current output to the steel reinforcement early on. That is it's actually encased in a stainless steel can, which you can just about see the edge of. And this stainless steel can acts as the current deliverer of the charge that's being developed by the battery. We have some sort of control. We have a kind of a diode that's inserted in the circuit, which stops the current being dumped onto the galvanic element early on, but then allows, it's like a valve, if you like. When the battery runs out, the current is allowed to pass to the steel through the galvanic element. And in the laboratory, we had a go at simulating this, and this is some of the results. We could induce quite high corrosion current densities from the battery, over 20 milliamps up to 40 milliamps and so on, but it's a reducing trend. This occasions when we were wetting the concrete and therefore delivering higher current. And here we disconnected the anodes and measured the polarisation. And this is the galvanic anode taking over. So you can see that there's a big drop in current output, but it's still within the level that is required for cathodic prevention. So it's the first very large amount of current delivery, try and stop corrosion, and then a maintenance of the galvanic element. And we had a chance to do this on a bridge structure, a column that corroded and forced some cracking of the concrete on the edges. Steel reinforcement is about here. The chloride level was up to about 2%, particularly at the regions where corrosion had occurred. So we saw this as an ideal opportunity to try the fusion anodes. Here's where we actually removed the concrete and reinstated the steel reinforcement, and we've applied galvanic anodes either side of this patch repairs on both sides of the column. Roughly, that was the sort of the layout of the galvanic anodes. Initially, we only connected the 4 anodes in the middle because we wanted to take some anodes out. In fact, we took all the anodes out eventually to see what happens once you put them in concrete. We maintained quite a high initial current, and the cumulative charge the first stage, we went up to about 130 kilocoulombs. So that took about 120 or so days to deliver. Then we took the anodes out, cored them out, and sort of fixed them, if you like, put them in a sunbox, and continued to. You can see that the stainless steel remained intact, which is one of the reasons we took them out. We wanted to see whether driving current through them, or through some of them, would cause any pitting on the stainless steel, and it was clear that that wasn't the case. And that was primarily because of the encasing mortar that was very highly alkaline. We then embedded them in a sunbox, connected them to individual steel bars, and continued to monitor them. And we can see that obviously the ones that were not connected up inside and then connected in the laboratory, they produced that initial current. Then there was a gradual drop, and then the galvanic anodes took over. And this is actually happening all by itself. So as soon as the battery runs out, then the galvanic anodes kick in and they maintain the lower current density. We then went back and included some more anodes at the same place. This one with the smaller batteries, because we'd already passed quite a lot of charge to the steel reinforcement. And that kind of summarizes the whole. It's a very busy sort of graph, but I'll try and break it up gradually. What we have here is the amount of charge that we delivered. This was the first stage, just before we removed the anodes. We then removed the anodes down here and introduced the new anodes, which had a shorter life because they were smaller batteries. They produced a charge as well. And this is the charge that's being produced by the galvanic anodes, which gives you a gradual increase of the charge delivery, which is the cumulative charge. Now, on the other graph, we have over here the depolarized potential, the potential 24 hours after each disconnection. And we can see that we started from a very negative potential. The steel was actually corroding at the beginning, but very quickly the potential had become very passive, even within this 120 kilocoulombs. We stopped at 120 or thereabout because that's what we found in the lab. We were able to stop corrosion at 2% chloride. We could see quite clearly that we passivated the steel considerably. Potentials have almost become positive. Even after we allowed them to depolarize a little bit, over this period, the potentials always maintained a passive potential. It didn't really matter that we applied the extra amount of charge in this case. The steel was passive anyway, and it just remained passive. So the passivation really was achieved by that very early initial charge. So we're still continuing to monitor this. It's coming up to 3 years now. As you can see, the steel is still passive. So conclusions. An initial charge at the top end of the corrode protection current density, i.e. a little bit more than 20 milliamps per meter squared. We tend to try and achieve about 30 milliamps per meter squared. Can arrest corrosion of the steel if you apply enough charge. The level of applied charge to arrest this corrosion depends on the corrosivity in concrete environment, i.e. the level of chloride primarily. And subsequently passivation of the steel can be maintained long-term with the galvanic anodes. So a two-stage process is thus achievable with the specially designed modular fusion anodes. And that's the end of the presentation. Thank you very much for your attention.
Thank you very much, Dr. George. That was a very interesting and informative presentation. And thank you for everyone who has questions. I'll go through the questions now. And in the meantime, if you have any more questions, please feel free to add them in the chat box. We still have time to go through a few more. So I will start from the beginning. So the first question, which has followed with a couple of more questions in the same field, is about actually the environment that the tests are done. Dr. Yunan Gao is asking, would the location of the site to carry out the trial have influences on the results? Apparently, Leicester is fairly inland, and the environment there is mild compared with the coastal places. And also, Stephen Tate is adding a comment related to this, that he thinks that the location is certainly important, and that the frequency of de-icing treatment by different local councils around the UK is also affecting the test and the criteria here. You have any comment on this?
Yeah, sure. To start with, this particular test was carried out under a bridge over a major road. I think it's the A50, just outside Leicester. The problem there was that there was I didn't actually go into the details, but there's an expansion joint right on top of the cross beam, and they applied de-icing salt, obviously, and they leaked onto on the cross beam and then down to the columns, and that was the cause of the corrosion issue. As I showed, there were about 2% chloride there. Whether there's a difference in environment and whether that makes a difference to the process, I think we can summarize that by saying primarily it's the level of chloride that causes the corrosion, and therefore on coastal sides you would have more chlorides. So if you have more chlorides, you would need to increase your current output to try and arrest the corrosion. So then these particular ones were put at a spacing of about 600. We would then design them to be at a shallower spacing, say 400. That would increase the current output and increase the level of charge that we would deliver to the steel reinforcement. And obviously, we would only go on to the second stage if corrosion is actually stopped, and we will monitor that to see whether corrosion has stopped. There is a sort of a way that you can go back and apply externally the current, more current output using the stainless steel encasement, which again I didn't mention. But if ever there's a need to reapply current, then that is also possible. I don't know if that answers the question.
Yeah.
Obviously, environment does make a big difference.
Yes.
As was shown. But we have now actually up in Scotland. Was the latest job that was on the coastal site, and we've applied, and we're monitoring those at the moment to see how we developed, and we're hoping to publish that actually in the next year. So results will be becoming available pretty soon. It's quite a new technology. The uptake has been a little bit slow, as you would imagine. Engineers need convincing before they start new technologies, or before they can trust new technologies. But our intention is to publicize all the results so that people can gain confidence.
Thank you very much. The next question is from Camilo Godoy Vargas. Can you please elaborate on the aging factor? Does it represent the time to have the anode current density?
I'm not quite sure what the question is. The aging factor of concrete?
Yes. Probably the aging factor of the anode, yeah.
Well, the aging factor of the anode?
Yeah.
right? The aging factor of the anode depends primarily on how much current you're drawing from them early on. And that's what we've learned basically. So what we advise now is not to maximize the current output that's coming out of the anodes. I put them at shorter spacing or use larger anodes so that they're not pushed to the limit when you first put them up. If you do that, the aging factor will be influenced and will be a lot less than if you were more gentle with the anodes, if you like, and allow them to work slowly. But you can still design a current density depending on the surface area of your anodes, because we've got a whole range of anodes. The surface area determines the current output of the anode. So you can design the current density that you want to apply, the combination of the anode itself, which has a specific surface area, and also the spacing between the anodes when you insert it into your concrete.
Okay, thank you. And then another question is, what standard was used to assess the performance of the CP system?
It's the European standard for cathodic protection. It states that you need to achieve 100 millivolt depolarization over 24 hours when you disconnect the anodes or the power source. In this case, I didn't actually mention the depolarization levels, but they were very close to 200 millivolts. So that during the first stage, that was very easily achieved. The second stage, once the potential is less negative than minus 150 millivolts, there's actually no need to follow the standard, because the standard itself mentions that the steel is therefore then passive. So you don't particularly need to apply cathodic protection, but we're applying cathodic prevention so that we don't go into a corrosion situation again. And cathodic prevention is not, although it's mentioned in the standard, there aren't any criteria still that apply to it, other than the current density needs to be between 0.2 to 2. The new standard, when it comes out, it will actually say 0.4 to 2, because one of the reasons was that I showed my results, it showed that when we dropped below 0.4, we were seeing corrosion of the adjacent area.
Okay, thank you very much. The next question is from Fuad Khushnau. Please, can you list the initial visible indication of corrosion occurrence, and what are the non-destructive methods to detect corrosion in concrete?
Sorry, I'm going to have to ask you to repeat that question. I didn't quite catch
so
it.
the first section, the first part is asking, can you list the initial visible indications of corrosion occurrence? And the second part is what kind of non-destructive testing methods you can use to detect corrosion in concrete.
Okay. Well, visual is obviously, if there's cracking of the concrete, that follows the steel reinforcement, and you could be quite confident that it's caused by corrosion. Often there's rust stains that tend to leach out within that crack itself. But if the concrete hasn't cracked, it's very difficult to know that corrosion has actually happened. And the best way to detect that is to carry out a potential map. I did show a potential map in one of the slides. What you do, you choose a grid on the surface of your concrete, make a connection to the steel reinforcement, and then using a standard reference electrode, you measure the potential on the surface of the concrete at this node point, and then you draw an equipotential map based on those results. And that will clearly show if there's a corrosion activity, you would tend to get potentials which are less negative than -200 with respect to a copper sulfate electrode. More likely if it's -350 or so. -200 is not, between -200 and -350, it's an iffy kind of area. There may or may not be corrosion. If it's less negative than -200, then the corrosion, you're reasonably happy that there's no corrosion. And if you're below -350, unless the concrete is starved of oxygen, i.e. saturated, then the sign there is that corrosion is occurring.
Okay, thank you very much. The next question is from Brian Wyatt, and his question is actually in 4 parts. So I will ask one by one. The first one is, you talked of a new minimum steel CD for steel in concrete. What value is this?
Minimum, sorry? Minimum.
Is CD Charlie Delta?
So current density.
Oh, current density. Yeah. Okay.
For what,
Yeah.
for what reason?
For steel in concrete, what value is this? You then proceed to talk of catalytic prevention current density. Is this 2 milliampere per square meter?
Okay. Well, that's I know Brian very well. I would attempt to answer these questions. It's the current density. If I understood the question right, the current density that we apply during stage 1, which is the ICCP element, is of the, it's got to be at least 20 milliamps per meter squared. Otherwise, you don't really get a buildup of alkalis around. Well, you do, but it takes a lot longer. So in order to achieve a quick buildup of alkalis around the steel reinforcement, you need to be above that level and preferably at 30 milliamps per meter squared. As that's shown, the higher the current density, the quicker you can achieve that. And that's because of the voltage gradient that allows the sodium potassium ions to be attracted to the steel. They are being supplemented there by the production of hydroxide ions, and therefore you've got alkali hydroxides. And also the gradient of steel of chloride tends to diminish as well, or the level of chloride tends to diminish the higher the current output that you produce. So you need to have conditions where you're constantly pushing the chloride away, constantly increasing the alkalinity in order to try and repassivate the steel. For cathodic prevention, I mentioned that previous work that we've seen and from periphery, etc. We mustn't really go below 0.4 milliamps per meter squared, up to about 2 milliamps per meter squared. Our aim is about 1 to 1.5 or thereabout milliamps per meter squared. Okay. So we'll design the spacing so that the galvanic element will produce that kind of level of current density.
Thank you. The second part of the question is, in your impressed current use, showing effects of polarization before the graph showing current density from 0 to 1000 milliampere per square meter, what steel current density did you use?
Can I go back to the slides? I mean, I'm not quite sure which. Repeat the question again so that I can.
Yeah. In your impressed current use, showing effects of polarization before the graph showing current density from 0 to 1000 milliampere per square meter. What steel current density did you use?
And
probably
if you'll
better.
allow me
Yeah, if you can. Yes,
permit me to speak. Sorry, George. If you keep sliding back, keep going back to your slides. Keep going back. Keep going back. I'll ask you when to stop. Keep going back. Right. No, back some more. Right.
Back?
In this, back. Yes. Okay. So in that graph where you're showing the effects of polarization, and I believe there was one before where you showed a whole that exactly. What steel current densities were they at?
Yeah, I believe it was 50 milliamps per meter squared.
50. Thank you.
Yeah.
I'm sorry about the complexity of the question.
And
I
okay.
Brian, can you continue the other sections as well? Yeah.
Man, if you don't mind, I'll be happy to do that.
Yes, please.
And I promise everybody that I've not changed my sex to Linda. It's an IT issue. Right. And you'll know why I'm asking this question, and I hope it'll make you smile. Could we use your data to inform the minimum charge for chloride extraction?
Okay. Chloride extraction is probably slightly different because there you're allowing, you just apply chloride extraction and then you stop. And subsequently what would happen is you would get possibly back diffusion. So unless you use capillary prevention to try and prevent the chlorides from getting back, the criteria may be slightly different to that. But I think the short answer would be yes, probably yes.
I think there's some really good stuff in here that we could in fact use, and you'll be aware there's a bit of a debate going on at the moment about the criteria for.
Yes, correct. Yes, I do.
Okay, and just to keep my as short as possible, and I think you may have answered it in one of your earlier answers. Do you have data on potential decay from all of these systems? So typically, as ISO 12696, the European standard, or the ISO standard for steel in concrete, you're 100 millivolts over 24 hours or 150 over longer. Do you have those data?
Yes.
Okay, no, I don't believe you showed them. I believe I've been awake for the whole presentation.
No, I haven't showed them. It's sort of a time issue, really. But privately, I'm very happy to show you anything you want to see.
Okay. I mean, thanks ever so much, George. As always, super presentation, and I've had more than my fair share. I'll go away.
Thank you very much.
Thank you, Brian. Okay. The next question is from Stephen Tate. He's wondering whether your fusion systems are being specified now for new build projects as well.
Yes. Surprisingly, it's become very popular in Australia. I'm not quite sure why that is the case. But we've had possibly about half a dozen jobs in the UK, and as many as that probably in America. But by far the most are actually in Australia. I think there must be somebody down there who's able to sell the idea a lot better than the rest of them.
Yeah, thank you. The next question is from Kenneth Mackey, asking why do you need the battery to carry out the initial passivation by ICCP? Would it not be cheaper to carry this out externally and make this good afterwards?
Yes, I don't think it will be cheaper. I mean, it depends on where your structure is and how accessible it is. And also there's the problem that your units may get vandalized if they're temporary. I mean, if you're going to go through the expense of making sure that nobody touches your externally applied impressed current unit, it may not be very cheap at all. I think this is quite an easy way of achieving that. You just you drill your holes, you put your anodes in, connect them, and just leave them. There's no need to go back and change settings or anything like that. You can monitor, but you don't need to do anything beyond that. The external supply, you have to determine how long you need to be applying it. Then obviously you have to be there to stop it and reconnect your steel reinforcement to the galvanic anodes. It's possible, but it's more elaborate, and I think depending on access, that could really make it quite expensive, really.
Okay, thank you. The last question at the moment is from Dr. Nigel Owen. He's asking for your disc-shaped zinc anodes. Can you change the shape of your sacrificial anodes to a slender wired rod to increase the current output so that this may increase the initial current output? Would the shape of your fusion anode benefit also from this?
Yes, and yeah, we're going through all that, all those considerations quite thoroughly at the moment. The fact that we can't really do a lot of laboratory work, giving us the opportunity to look at all the product and try and redesign. And those are some of the things that we are doing. We actually do have long rod type anodes. We call them DAS anodes. And like I said, the current output of the anodes would depend on the surface area of your zinc product. But you also have to be aware that, you know, if you use too many fins or what have you, that they would preferentially be corroded compared to the bulk of the anode. And, you know, the aging factor would be determined, would obviously be very different. The aging process would be very different. You would use up a lot of the zinc because of the edge effects of some parts of the anode, and then the current would drop down suddenly to when it becomes more of a uniform shaped anode beyond that. So these are all being considered. We are doing a lot of modeling as well to understand all these. We have learned a lot really over studying the 20-year results, not just of that side, but as I showed before, there's at least 12 to 13 that we've been monitoring regularly across the world, some in America, some in the Far East, some in India, and they're all showing us different aging phenomena, because if the temperature increases, it appears that that doesn't affect, if the increasing current is due to an increase in temperature, the aging factor doesn't seem to be influenced as much as if you were in a sort of a cold climate, you had a wide spacing and forced the anode to produce that extra current. Because what we found is that the current output is related to the Arrhenius equation. So if you plot logarithmic, the log of current versus the reciprocal of temperature in Kelvin, you get a straight line, and it shows you that for every 10 to 15 degree increase, you're doubling the current of your anode. So if your mean temperature is about 10 degrees, which tends to be in the UK, and then you go to Florida and it's 20 degrees, you would double the current output of those particular anodes. But if you set them at the same spacing, the aging factor would not be influenced in that case, because the diffusion also is dependent on the temperature. So migration of corrosion products away from the interface is equally increased. Therefore, the net effect is basically zero. I know I've talked a lot over the top of what I was supposed to say. I hope it answers the question.
Yes, definitely. Thank you very much. And I think with that was all the questions in the chat box. Thanks everyone for asking questions, and thanks a lot for your excellent presentation and taking the time to answer all of the questions in detail.
Absolutely. Thank you very much for inviting me.
And with that, I'm handing over to Dr. Ijaz for closing remarks.
Cheers. Thank you very much, Ruman, and thank you very much, Dr. George. I gave much appreciated for your interesting presentation, and the sign of the good questions came about, which shows that the presentation was well received. I would request all of you to put your virtual hands together and thank Dr. George. Just few quick announcements. Just first one is the survey that we would be sending out a survey link to all of you who has joined, and thankfully for staying us this and up this time as well. Much appreciated. If you require or request any of the CPD, please mention your email, and then we will hopefully send you the CPD soon after that. Another quick announcement is for the request for presentations. We have requested that to all of our sponsors, as well as we have requested into general public. If you or your company or anybody in your organization want to present, please feel free to contact us as soon as at icorrabz@gmail.com, or of course me or Amir, who has sent you email to join this presentation. Please feel free to reply back to that and submit your abstract before end of April, which is our deadline for next year. I have noticed that the change in clock, especially in UK, has caused a bit of confusion internationally, and some people joined us an hour later. Apologies for that if it may have caused any issue, but be informed that this session has been recorded and that would be available on YouTube soon. Hopefully within the next 2 weeks. Please feel free to share it with anybody you feel that they'd be interested in the presentation, and of course the link is available in one of the spaces you would see in ICorr Aberdeen online anyway. And the next event, which is not formally confirmed yet, but it was advertised as ICorr MCF joint event in April. Because of the COVID situation, we were hopefully initially thinking that if it could be a face-to-face event, but apparently it is not going to be because of the recent Scotland COVID guidelines. We would be probably organizing something similar to what we have done last year, and early this year with MCF, we would probably organizing some sort of webinars, but the program is still there. We would be hopefully organizing soon. Please watch the space. We will be sending you email with the whatever the updated program. You wouldn't have to travel, therefore there will be a lot of parking space. You would be happy to join us on hopefully a 12 o'clock presentation as time, and I would be very happy to see all the international audience we are receiving over a few months, and thanks to those who have joined us from all over the world, and thanks to our presenter today, Dr. George Sergi, much appreciated. With that, I would close today's meeting, and thank you very much, everyone, for joining us. Much appreciated.
Thanks, everybody.
Thanks, everyone.